what you guys learned about was you learned about the 3 types of bonding. The first type was the most complicated type of bonding. It was ionic bonding. And ionic bonding is unique because it actually requires us to do math, okay, to understand how to build a proper valid formula, okay, a proper valid molecule. And the biggest characteristic about ionic bonding that you need to know at the chemical level is that it's a transfer or exchange of electrons. You get a full charge because you fully lose or you fully gain an electron, and an electron has a negative charge. So if you fully lose an electron, you now fully carry a more positive charge. If you fully gain an electron, you now carry a fully negative charge, right? And so that's the big idea. And electronegativity helps us kind of predict basically opposite sides of the table merged together. Or another way you can think about it is metals and non-metals. Metals way over on the left and non-metals way over on the right tend to merge together to create a full transfer of electrons and therefore an ionic bond that makes an ionic compound, an ionic particle. Okay. And we talked about, like, we looked at the metals first, and then we that serve as the cations, the positive carrying atoms, right? And then we looked at non-metals, the negative carrying ion, right? The anions, right? The negative part of the bond. All right. And there was a really unique thing about metals, particularly that transition metals, okay, don't have a set charge. When you look at the periodic table, okay, columns 1 and 2 are really easy to predict. If the end goal of bonding is to get to access an octet, to become somewhat like the noble gases electron configuration wise, okay, it's easy for us to understand why column 1 and column 2 elements will lose 1 or 2 electrons to take on a more positive charge. They'll lose 1 or 2 negatives and become overall more positive, right? And it's easy for us to understand why the non-metals will gain because they're closer to going forward, right? It's like an airplane, right? Find the exit nearest to you. It could be behind you or in front of you, right? So for non-metals, for noble gases, or sorry, non-metals like halogens, an oxygen column and nitrogen column, it makes sense that to become like a noble gas, it'll gain electrons because it's easier to just gain than lose a bunch for them, where depending on their location on the periodic table, which by the way, everyone should have their periodic table out. I don't know how you're doing this class without it. Okay, so that tells us something, but transition metals are weird, which is again one reason why we don't blame Bohr for ignoring them. Okay, Bohr had an idea. He's like, right, if it's like many things, right? If there's a problem, if you just don't look at it, it doesn't exist. That was what the method that Bohr took. And there were a lot of problems with transition metals. They're weird, they're colorful. Okay, they're like the crazy cousin that you're just like, you know what? It's better if you just stay over there, right? Like, we appreciate you to stay right over there. Okay. Transition metals are weird in the fact that when they form ionic bonds, right, they don't take on a specific charge always. They always carry a charge if they're an ionic bond, but you can't be like, it's always going to be a 2. It's always going to be a 4, right? It's more like it's going to be what it's got to be, depending on what it's partnered with. Like if it's partnered with a total -4, okay, oxygen 2, then it's going to either be by itself a +4, or it's going to be maybe 2 +2s, or maybe it's going to be 4 +1s. Okay, and it kind of just kind of does what it needs to do to make it happen. And so for that reason, that's why when we write the name out, when we write the full name out, we write the Roman numerals. So one thing to help you remember when to write the Roman numerals, which is never in the formula, never in the shorthand. Like you would never write iron to oxide. Like that's no. That's like a no. Okay. You would never do that. You only write the Roman numerals when you're writing the full name. Iron to oxide, right? A good way to remember is it's like a British name, okay? Or like I know that it's actually British is the best example, right? Henry VIII, right? If we're writing the initials of Henry, the awful king, what was his last name? Henry what? Does anyone know? Okay. Okay, Henry, let's say his name is Kierkegaard. I don't know, some philosopher. Henry Kierkegaard, okay? We would write HK. But if we wrote out his full name, we would write Henry VIII, right? It's a good way to remember is Roman numerals are only used when you're writing out the full name, right? If I have 3 names technically. My name's Allison Yanmeiju Judy. Okay. My Chinese name is my middle name. And then I have 2 first names and 1 serves as a last. Okay. And let's say I was the 5th. Okay. I was the 5th of me. All right. I would do my initials are AYMZJ. Okay. And if I would give my initials, I would not tack on the 8th at the end. But if I were to write out my full legal name for, I don't know, Social Security purposes, okay, I would have to write out all of that, including the 8th or the 5th or whatever. Okay. So that's just a little reminder. It's a common point loss when people put Roman numerals in the formula, in the shorthand. Don't do that. We don't need it. Okay. So that's just like a little intro to or review on ionic bonding and the special nature of transition metals. So out of curiosity, okay, let's look at your example problems from your warm-up. So I kind of went over the characteristics of ionic bonding for you. It is your responsibility to study that. Like that is your trick. My biggest suggestion would be, remember, it is almost guaranteed metal plus non-metal. Or the moment you see a polyatomic ion bonded, ionic. Like the moment you see a polyatomic ion, which means you had to have memorized them well enough to spot them. You had to have known them in your brain that you can see them. Okay, but once you see them in a bond, bam, ionic. Just hands down, boom. And here again, remember, hydrogen we treat like a metal. We treat it like a metal because it's so far to the left where the metals are. Okay, but let's do our warm up. Write the formula or the name. So for A, Li3N. What is the ionic name for that, Liam? Lithium nitride. And if remember, I'd like to make a bond with you. That last syllable in the second element, the anion, is transitioned or transformed into I'd. I'd like to be a bond with you. If I just wrote lithium nitrogen, it sounds like I'm naming 2 separate particles. I'm like, hey, there's lithium, there's nitrogen. Whoop-de-doo. Right? But it's like kind of like adding Mr. or Mrs. or like a married couple, right? You connect them somehow. So I'd like to make a bond with you tells me that lithium and nitrogen are now in a bond. Now, what must the charge of lithium be? What must the charge of lithium be? Plus 1 plus, Min. How about nitrogen, Juan? What's the charge of nitrogen in an ionic bond? What charge does it take on when it does this method of bonding? Look at your periodic table. What charge does nitrogen always take on when it is in an ionic bond? 3 plus? It gains 3 positives? -3 or 3 minus. So that tells me why in my formula I needed 3 lithium. I need 3 lithiums for every 1 nitrogen so that my charges cancel. 3 times +1 gives me +3 plus -3 gives me 0. That is merely a mathematical indicator that you did it right. That's all it is. It's a mathematical indicator that you did it right. You exchanged well. Okay. If I am a person with 3 friends that have $5 and it costs $15 to buy something for us, a shared meal, you better bet your bottom dollars that that cashier is going to be like, either way, man, however you get it, you need to owe me you need to owe me $15. So whether it's 3 of you paying me 5 or 5 you paying me 3, I need 15. That is an indicator. Whatever you lose, I gain, and it should equate to one another, right? So, excellent. How about B? What do we got for B? I think I asked for the formula. Haley. Okay. +4 charge. NH4. What else? What's the rest of it? Okay, NO nitrite. Okay, I see what you're happening. Down here, nitrite is a NO2 with a 1- charge. That's a little 2. Okay, so let's go over this. You have the parts. You have an NH4 and you have an NO2-. Okay, now do we actually write the charges in once we're bonded? No, it's kind of like saying, right? Like once you've I don't know, traditionally, once you got married, you changed your last name traditionally, not in East Asia, but like here in America, you change your last name. Kind of would traditionally be a little bit weird if you kept your maiden name and like hyphenated it. Okay, some people do that, but that's a little one, that's terrible paperwork, by the way, like awful paperwork. Okay. But two, really annoying to write in on every form. Okay. And three, it kind of weird. You're like, well, why'd you keep, if you're now bonded, why'd you keep it? Traditional marriages, right? Same idea here. We don't write the charges once we're in a bond. We assume that you knew them and you were competent on the polyatomic, that you could figure it out. Okay. So that being said, you have the right parts. NH4 ammonium with a +1 charge, NO2 minus nitrite with a 1 minus charge. What is the ratio between those two polyatomics when they bond to cancel out? What's the ratio? How many of each one do I need to cancel out? 1 to 1. So all I do is for my formula, pull it in a little closer. Bam. NH4 NO2 minus. And that, my friend, requires you to see that. Do not try to say, oh, nitrogen tetrahydride, nitrogen dioxide. Don't do that. You have to be able to see the polyatomic. So that's a big thing about memorization is there's some things you just, and this is a memorization heavy unit. This is like the worst it gets, okay, this unit. Because you're going to get a series of things to memorize that you just have to. You just can't create a shortcut. It just is what it is. Okay, how about C? What do we got for C, Alex? Magnesium chloride, and that is perfect. Okay, magnesium chloride is not a transition metal, so I don't need to tell you in Roman numerals. And I don't say dimagnesium dichloride or whatever. It's ionic bonding. I assume you can do math. Okay. Yes, Carlos. The charges, because I assume once they're in a bond, I don't need to say that anymore. If I keep the charges, it's like saying it's separate. It's like saying these two ions exist near each other, but separately. But they're bonded. So I can remove all that self-identification. We are now one. Okay. So magnesium chloride, not chlorine, chloride, like to be in a bond with you. I am now officially together. Okay. How about D? Min? CU, 3 of them, P2. Excellent. How did we know that? I was told in my name that I have a Roman numeral 2, which tells me that copper kicks on a 2+ charge. But phosphide or phosphine, phosphorus, what in the world? Phosphorus always takes on a 3- charge. So I know that in order to cancel out, 2 and 3 don't cancel out. That's not right. So I have to find the common multiple, which is 6, which is basically multiplying by one another. So I say, well, times 3 gives me +6 and times 2 gives me -6. And that is where I get my little subscripts. Notice these are small numbers. Please, for the love of all that is good, do not write it like this. That tells me that's an assay, probably with a biochemical aspect to it that I don't even know what you're talking about. So this isn't real. That right there is not a real thing. Now, make those tiny. Now it's a real thing. Okay. And it should be tiny because it makes sense that, like, you know, the big important part is that they're bonded together. So don't let the numbers steal the show, right? Keep them small, keep them tiny. Okay. Awesome. Okay. So everyone feeling a little bit better about ionic bonding, kind of a little bit. Danny, what's holding you up? Yes. With the, yeah. What about the charges on your periodic table? Like, you guys can add charges onto your periodic table. Like, that is totally fair game to add onto your periodic table charges. For carbon, it's ±4. I will tell you a little secret. Carbon almost never engages an ionic bond because of that. It's so ambiguous It's very rare that it actually does an ionic bond. Carbon's more famous for covalent bonding. It's more comfortable doing that because there's no real win for it. There's no real clear win. So sharing is actually a much better option for carbon. And that plus or minus for life is part of the reason why. But yeah. Okay, so let's move on to covalent bonding. Oh, yes, Mika. Based off the anion. So let's say I gave you some compound like zinc, okay, F2, fluoride 2. Like that's the formula. I'm telling you that is correct. Like I'm not telling you to make a new one. I'm telling you that's correct. So I know that fluorine always takes on a what charge? A -1 charge. I have 2 of them. So what's the total amount from the anion, the negative charge? So then what must 1 zinc be? +2. Now, what if I told you it was zinc 2 F2? What must the charge of zinc be if, again, I still have that -2 total? To have my charges cancel and I need 2 of them? 1, exactly. So you base it completely off of the known one, which is the anion. And that is a different compound. That is not a real compound, but that would be a different one if it did exist. So it's just math. And for some of you, that's your worst nightmare. So I do apologize. And it's math unspoken. It's unspoken math. We expect you to see the math. So here's what I would say. If you can't see it, write it. Show it to yourself. You don't have to keep it unseen. Put it somewhere so you can see it, right? Right, we're all about evidence. Prove to yourself that you know what you're talking about by putting it down on paper, okay? Okay, so let's move on to covalent. Polyatomics, that is just straight Quizlet, baby. That's just Quizlet, okay? Big idea, though, of course, is that you put a parentheses. For the love of all that is good, please do not forget to put parentheses. If you have more than 1 polyatomic and you forget to put the parentheses, we're going to have like 42 oxygens attached to 1 atom, and it's going to be very concerning, okay? It's going to be very, very concerning. No one can handle that many oxygens, okay, and still be alive. Yeah.
So with the parentheses for the polyatomics, why don't we just multiply it and just say 12 oxygen?
Because that is a different compound.
Oh, yeah.
Yep. There is a reason you have the ratios that you have. And even if the total amount of atoms end up being the same, the way that you organize them matters, right? Kind of like how you organize your room. All of your crap in your room stays in your room, but where it goes matters. How you group it up matters. It changes how you interact with your room. It changes the stuff that you can do. It's all there, but it's set up differently. And that setup is super important. Okay. That setup is determined or represented by your subscripts. How did I organize those atoms? What combo did I do it in? They're all there. Just how did I do it? Okay. So, okay, let's move on to covalent. This is so much nicer because it's sharing is caring. And it's all about, well, I don't need you to give me those electrons. I just need access. Like sometimes like, right? Like, one of the things that me and my friends do is we all own cars. We drive. When we went to Disneyland, the last thing I wanted to do was drive. Okay. I just needed access to a car to get there. It doesn't have to be my own car, right? Same thing with covalent bonding. It doesn't have to be their own electron. They just need to be able to have access to it when they require it. So what they do is they share their electrons to get to an octet. They don't need a full ownership because that's a lot of responsibility. Car insurance, okay, it's expensive. You get into a crash, you pay for that. Your friend ain't going to pay for that car accident. That car's registered under you. They're going to be like, bummer, even if it was their fault because they distracted you, okay? They ain't going to pay for that. There's a lot of responsibility for carrying a full ion, right? There's a lot of responsibility for that full electron charge. So sometimes it's just better to be like, hey, man, I'll pay you for the gas money as long as I get access to that car. As long as we make a little deal that benefits both of us, it's all good. It's all good. That's covalent bonding. It's sharing. Okay. And so what we see is we saw a couple good ones. Again, this is memorization right here. Diatomic molecules are an excellent example of covalent molecules because they share. They're sharing with themselves. They're like, bromine can never exist alone. When you think bromine's alone, it's not. It's with this identical twin. And it's sharing electrons. there's no charge actually being taken here. So what you'll notice is a lot of elements that typically take on charges no longer take on a charge in covalent. Charges only apply when you're ionic. Okay, that's why in the homework, I had you guys identify the type of bond, ionic or covalent, before you tried to name it. Because once you know the type, you know how to name, you know what rules to follow. Okay, so, and you can have multiple, single, double, triple, whatever. Okay, and here, because you can't exactly have a charge, you can't do math, we just have to straight up tell you how many there are, which is actually kind of nice because it removes the thinking from you. It's just like, look, man, I'm not even going to try to have you figure it out. Here's what we know. Okay. And what we do is we use Greek prefixes. And if you've ever read a book and you've looked at the table of contents, you will see Greek prefixes. Okay. Wait, I'm thinking Roman numerals. If you've ever taken geometry class, you will see Greek prefixes. Okay. Triangle. Okay. Tetra something, hexagon, heptagon, septagon, whatever. Right. So hopefully you both read a book and done geometry. That's the end. That's the big idea of this conversation. For the examples, let's see for the warm-up problem. Okay. I asked you, I did just simple because I figured you could do this. Sulfur trioxide. What's the formula for sulfur trioxide? Oh Lord, there it is. Oh Lordy. And normally, just like normal, we put the more positive in front and the more negative behind in second. But it's not a for sure positive. It's just a more positive. Okay. What about B? What was the formula, Matthew? What was the name? Sorry, for B. Matthew's got it. Oh Lordy, where do you think we're at?
I have no idea.
Think really back to your like short-term memory. You got this. What was I just talking about? I even had Liam answer one of the questions. I moved on from one type of bonding to the next. So where are we at? 4. And where are we at within 4? B. So tell me, what is the name for B? For B. Look at your covalent naming rules. Silicon or silicone, either way. What is it? What is it? If you want to call a friend for help, okay, call a friend, put them on the hot seat. I know. Someone over there has got to know. You got this. You got this. Bryce, you got it? You're so close, but remember it's covalent. So there's no actual math that can be done to tell you that ratio. So I have to just tell you it using Greek prefixes.
Silicon chlorine.
You not the right. It's not bi, it's di. You're so close. You're so close. We have all the parts. It's just need to put together. Silicone, di, chloride, silicone dichloride, silicone dichloride. Okay, silicone dichloride. Okay, so Matthew, stick with me. Stick with me. Okay, so you were absolutely right, Bryce, when you said chloride. But if I just say that, then it makes it sound like I should know what the little number is. But I can't because I'm sharing electrons. So I just have to tell you. So that's why we say di. Now, bi is not used here, okay? This is Greek prefixes, not Latin. Okay, so we use di. Okay? All right. So, dichloride. Excellent. So, why am I not erasing? Okay. So, any questions with that? That's kind of like my little overview. My little overview. Okay. All right, so now we're going to continue on into our discussion about how do we illustrate particularly sharing of electrons. So Lewis structures are the illustration of how atoms share electrons. So what type of bonding is that if I say share? Covalent. How atoms share, particularly not just any electrons, but valence electrons in covalent molecules, or covalently bonded, right? Structures, covalently bonded particles. Keyword here is covalent and share. Those are your keywords, covalent and share. Okay, and so here's a little kind of key to how we draw these. Every dot equals one valence electron. Every line represents a bond between two valence electrons, and B/W means between. It's old school secretary language, okay? So we have a couple rules that we already know. How do we make sure that we draw these correctly? Well, for hydrogen and helium, we need to make sure they have access to two valence electrons. VE is shorthand for valence electrons. And for octet rule, it's most all atoms will want to have access to 8 valence electrons, right? Like the noble gas. So we're going to go through one example of how we draw this, and then we're going to start tomorrow on this fresh, okay? But I just wanted to get it in now while you're thinking about covalent bonding. So let's take ammonium. Step 1 that we do is we count the total valence electrons that each atom in the molecule brings. So nitrogen starts with 5 valence electrons, and I have 3 hydrogens, okay, which tells me that each hydrogen is going to bring in 1 valence electron. So right now, in terms of the amount of valence electrons being shared, I have a total of, okay, 8 valence electrons being shared within this molecule between the 3 atoms. Okay, so what I do is I do step 2, draw the skeleton is what we call it, the basic bare minimum bonding. Like, how do these connect at the very least? Like, they have to all be connected somehow if they're in a bond. So what we say is we typically put the first element is the center element. And then we say everything around it is like it spokes on a wheel, okay? So we say nitrogen's the first element. So I'm going to put nitrogen in the center. And the bare minimum bonding is it has to be bonded at least once to each of these, what we call terminal atoms. So hydrogen here is what we call a terminal. It's on the outside, terminal atom. And the bare minimum bonding is, okay, it's got to be at least bonded once to each hydrogen. If it's not bonded at least once, you have a problem. It's not bonded, right? Step 3, okay, is now you redistribute remaining. Okay, valence electrons. So what you notice is each bond represents 2 valence electrons being shared. So what's happened is I've used 6 out of my 8 valence electrons available to me. So now I have 2 valence electrons remaining. Okay, that's my count right now. It's 2 valence electrons remaining. I've used up 6 out of the 8 for the other ones. Okay, so what I say to myself is, well, my structure currently is this. And I need to look and say, okay, well, according to the duet rule, right now, hydrogen has its duet. It has access to 2 through that bond. This hydrogen also has access to 2 through that single bond. This hydrogen also has access to 2 through that single bond. Now let's look at nitrogen. Nitrogen has access to 2, 4, 6 valence electrons, but it wants 8, right? So how are we going to do that? Well, what we're going to do then is we're going to say, well, I have 2 remaining valence electrons. So I'm going to move those 2 valence electrons to be to nitrogen, and there's nothing to bond it with. It's just what we call a lone pair. It's just sitting on that nitrogen. And now nitrogen has access to 2, 4, 6, and 2 of the 8 are its own. And that is what we call the actual structure of ammonia. And notice I've used up all of my valence electrons. So now I'm at 0. I've used all 8 valence electrons. All right, so that's today's intro to Lewis structures. Tomorrow, you will have a full lecture on it and then a new project.